So it's Sunday and we had an error at the antenna. So the antenna stopped and I have an error output in the log file. To find the source, I have to search the log files if this error appeared earlier in other sessions as well. But we have a lot of log files and we have a lot of error outputs. If I want to search, I have to read all of these log files, and this is a lot of work. But maybe computer science gives me a chance to do it in a faster way. The solution is regular expressions. And regular expressions are nothing more than a solution for formal languages. So we have to learn a little bit about formal languages to get these errors in a very comfortable way. So let's see how this input can be interpreted. And let's learn about formal languages and language theory. Welcome to the next lesson. Welcome again to the next lesson about programming languages. We have now a lot of things which define the hardware of a computer. So we started with a general description of numbers, then we brought these numbers into circuits so that we had we have a hardware available which represents operations on these numbers, on this numerical system. And then we created more or less complex structures like memory or adders, things like that, which are combined then together to John von Neumann architecture or a similar architecture where one central part is the CPU, the central processing unit. And there we have this algorithmic logic unit. And with this, we can start programming. And we started programming using mnemonics so that we were able to define a sequence of commands to individually adapt the behavior of this algorithmic logic unit. And then we came to the conclusion that we need something which hides the specific hardware parts, so that we created an operating system. And we define things, what is needed for an operating system, so scheduling, user management, rights management, all of these things. Everything with basic knowledge of programming, with a basic programming language. But for higher things, we need more than that. We need a better description of tasks which we want to do. And therefore we need high-level problem-oriented programming languages. And this is what we want to see today. So if I think about languages, I have to think about things like what are languages. So we will discuss problem-oriented computer languages, elements of a problem-oriented language. Then we want to classify the languages. And then we have to discuss if we have this language available. So if we can define words or sentences with this language so that we have commands, then we have to convert this again to a real workflow or a real sequence of assembly or machine code on the computer. So we have to do the compilation and linking, and then we can have a look on the different types of languages, so that you get a feeling, because there are so many languages and they can be classified, but some parts of this language are these languages are very similar. So this is what we want to do today, and therefore directly let's start with the discussion about what is a language. So we started with this here. So if you watch this is our assembly code, and if you remember, we discussed that there are some advantages and disadvantages. So we had this situation that we had a lot of advantages. So we were able to program, the mnemonics are easy because they are easier than the zeros and ones of a machine code, but they are not easy enough, because if the issues or tasks which we have to solve become more and more complex, then the structure, like what you see in assembly, become really unreadable. And therefore maintenance is bad, the portability is bad, because assembly is very specific to the CPU on which it is running and things like that. So there is a real need for these higher level languages, and therefore we have to define what is a language. A language is defined by syntax. So it defines rules which must be fulfilled so that a word or a sentence is understood. And the word itself contains signs or characters or symbols which are combined according to these rules. So first of all, a language must have an alphabet and must have a syntax. And then this combination of this alphabet and syntax, and a little bit more, so that we know when a sentence starts, for example, so that we can logically identify or describe what happens first and what comes next. We need a definition of a grammar. And in our cases, for computer languages, we do not take care on human languages or complex languages, where we have a lot of exceptions, like with articles in German language, so that you have a lot of exceptions like that. We just focus on formal grammar. So a formal grammar is a precise description of a language based on the alphabet, so on the symbols, and combined with the syntax, so that we define a set of rules and a starting point and an acceptance point to identify if a sentence or a word or whatever is allowed in this language or contains or is part of this language. And then there is another step. So this is a big difference between syntax and semantics. There is another step where syntax just defines the formal correctness, but to understand or to interpret, we have to also understand the semantics, which is the meaning or interpretation of the word combinations. So a sentence can be true, so that it fulfills everything, like in English, so that you have a correct setup of verb and substantive and so on, but it must not make sense. So it is, in the human sense, senseless. So, and this is the big difference. So syntax just checks the logical combination, and semantics checks if it gives a sense. So let's do a practical sample that we see this difference. Let's start with a human word and what we need for that. So in this case of a human word, we have an alphabet which is based on the characters in upper and lowercase. So our alphabet, our pool of signs, is the alphabet. And then we have a possibility of combinations. This possibility of combinations are the different words. So, for example, a combination APPLE combines to the word apple, or PEAR combines to a word pear. And all of these combinations are then the formal grammar, or in this case the grammar of the words. So all possibilities which are allowed. So apple in this case would not be part of the German language, because in German language apple would be Apfel. So apple would not be part of the German language, but it is part of the English language. But then in this point, apple, or the word apple, has no combination to the meaning. So in this point it's just the formal correctness. So it's similar to what I explained about the numeral system. So in the numeral system you have this representation, which is just the orientation of the characters, and then you had this calculation where you got the value, or the value of this number. And there is a big difference. So the combination, which is just the representation, and the value, and here it's very similar. So you have here just the representation, so the combination of the words which follow the syntax, so that is correct according to this grammar. So there is no meaning at this point, but we as humans directly convert this to this image. So this conversion to the image in our brain is exactly what is then the jump from the syntax to the semantics. And therefore there is a difference between syntax check and semantics check. So this is the correctness of words according to the grammar, and this is the correctness of the meaning, or of the interpretation, so that you see an apple or a pear or a pineapple, so that you convert the word, the pure sequence of characters, to a real image in your brain. And to represent now these, let's say, logical combinations, so these allowed combinations, this sequence, you can do the following. So you define a word like this. So let's start with this apple word. So what we have is, we have a starting point. So the apple must start with A, but there are several other words which start with A. So then we contain, so the next part is a P, and the next character is again a P, and so on. So you have a combination like this, and it is directly something like a graph, what is called a graph. And therefore the main important part to represent languages are graphs and the graph theory. So you will come to graphs later on again if you describe situations, for example, for robots or for high-level programming languages. For example, if a robot moves forward and then it finds a congestion, so it stops, and then it has to do something different. So it changes a state, so that it turns, for example, or things like that. So you can also describe this: move forward, the first state, and then you turn. So it's the next state, or the next edge to the next state, and then you continue with things. And the same is here. So you have a starting state. So at this state, all words start. And then if we have an A, we follow into this direction here. So A is this. If we don't have an A, for example, if you just check apple and not the other words, it would be like this. If we have an A, so if we follow this, then we can continue. If we don't have an A, we have a wrong situation, and we directly go to an error situation, so that we can identify, oh, it's not the word apple. It's not the meaning. So it's just a word, just the checking of the correct setup or the correct sequence of alphabetic characters. And then we continue. So if we found an A, we are in a new state. And therefore, we directly see the parts of a graph. So we have these circles. The circles are our states, so our positions from where we get a new character or where we make a new decision. The decision itself is represented with these arrows, and these arrows are then the so-called edges. So we have states and edges, and the edges are the decisions which we make. So what will follow? If we are in this position, then if we have a P, then we go to the next state. If we have a P, then we go to the next state. If we have an L, then we go to the next state, and so on. If we don't have this, then we directly go to the error position. And then, if we complete our word, so if we found a word which is accepted, then we have this double circle here, which represent an end state. So this is the accepting position. So at this point we accept the word. So at this point the word is correct. So, and therefore you directly see what we need for the description of a formal language. We need a starting point, we need a sequence of intermediate states, we need this decision, these edges or these transitions, or how we would call it. So this ways from one starting point to an accepted end point, to an accepted end state. And if you watch this directly tells you why these graphs are so important. Because there is no state or no situation which is not directly shown here in this graph. So for example, for robots, if they just follow this pure graph here, so they will find an apple or no apple. So there is no error situation which is not represented in this graph, and therefore the state machines or the state charts are very, very essential, not only for the language theory, but also for the description or the representation of behaviors in programs. So that you define, for example, for a machine, all possibilities, and if this possibility is not given, then you go to an error state. So you cannot forget anything which might lead to a situation where your machine crashes or something like that. So again, let's see what we need for the language, or for one special language, which is the simple word combination. It's written here. So we have an alphabet. This alphabet are in principle the labels on the edges or on these transitions. So in my case, lowercase characters. Then we have a starting point, which is represented with this circle and an incoming arrow. So the start node. Then we have a finite set of intermediate steps or states or nodes. Each found alphabet sign, which forms a dedicated word, goes to the correct endpoint. If we don't find it, we go to an error situation. And then a finite set of reach states in the word, which define the different steps from the beginning to the end point, and one or more final states. So we have one starting point and we have one final node, and one or more final nodes, and therefore we have paths through this graph to these final nodes. So mathematically, or in a more formal sense, it looks like this. A grammar is a fourth tuple based on a finite set of non-terminals. Non-terminals are replacement patterns or variables. They represent different types of phrase or clause in the sentence. Then a finite set of terminals, which are the alphabet signs or the combinations of alphabet signs. Then a start point or start variable, and a finite set of production rules, which are then the transitions from one point to the other. So which do a transforming in a way that we convert an existing part to another part. So, for example, if we go back to the graph, then we will have the following situation. So, do you remember? This is the graph which has a starting point, a lot of intermediate nodes, and then an endpoint. And you can now split this conversion or this representation into following steps. So, for example, you do the first part here. So, the first setup is A and a rest. The next setup is P and a rest. So, you have a starting point, which is A and a rest, and then you replace the rest again with P and a rest. So, this means you can convert this graph into a description, into a formal description of a rule set, which looks like this here. This means we have a starting point, and we replace the starting point by A, which is our terminal character, and a rest. And the rest is a non-terminal which can be replaced again. So the rest is this here. And then we replace this rest again with P and a rest. So we have P and again a rest. And then we replace this again with P and the rest, and so on. So that we always have combinations of terminals and non-terminals, where terminals are part of our alphabet and non-terminals are the rest which we have to continue to replace. Until we reach a situation that we just replace without rest. So that we just have a simple replacement with a terminal. So it's shown here. And this is our acceptance state. So this is what we then get at the end of our complete replacements. And therefore, a graph can also be represented in a written form like here, which is then the formal grammar, what you see in the definition of our formal grammars. So, what does it mean? We have this setup so that we have the rule set what you saw before, which makes A, AP, APP, APPL, APPLE, and where we have a starting point, intermediate transitions, and then an end replacement. So if you watch this, you always replace the left part with the right part, or by the right part. So what do you have? We have, again, like in the graph, we have a start state. The start state in our case is a start symbol, which is a non-terminal. So non-terminals are always symbols which will be replaced in further steps. So the start symbol is a very specialized symbol because there is only one start symbol allowed, and it is characterized with this underline. And then it is a non-terminal. It is part of the non-terminal symbols, and this non-terminal means that it will be replaced. And then we have a set of terminals. Terminals are part of the alphabet and describe what is the next replacement in case of a character. And then we have these transitions, so which tell us replace left by right. So replace the left non-terminals by the right sequence of a combination of terminals and non-terminals. And then we have logical combinations, which means that we have AND or sequence, a concatenation, and that we have OR, which means this or this. So in our case, we do not use the OR for this apple sample, but we use the concatenation, so which means this in combination with the rest. So A in combination with first sign OK. And this is represented with white spaces. So it's a concatenation symbol. And then we directly define our first grammar, because this grammar is one of the easiest one, or of the most basic one which you can find. If you check this, we just have rules which look like the following. So we have a left part and we replace it by a right part which contains a terminal and a non-terminal. So we always have this situation. We always combine terminal 1 and non-terminal, and we replace this non-terminal again with a terminal symbol and a non-terminal. So we have always the same style of rules until the last rule, which is just a replacement by a terminal, so by a character from the alphabet. So what do we have then here? It's a simple rule set which you can find here. If you have the situation that you replace a terminal with a non-terminal with a terminal and a non-terminal, or a non-terminal with a terminal, then you have the language which is called regular languages, or which is called a regular language. And if you remember the intro, I talked about regular expressions, and therefore regular expressions are part of this language, and therefore it's one essential element to have these regular expressions. And an algorithm or a program which understands or checks these regular languages or these regular expressions just follows the graph. So this means that we can write a machine which is called a finite state machine, because we have a finite set of states from the starting point to the end point, which understands or which checks if a word is part of a predefined grammar according to the regular expressions. So it just follows the states. So and therefore it means we have a machine which looks like this. You have an input tape, or you have some input mechanism where you take always the first, and in my definition I always start here on the left part and go to the right step by step, and you always continue with the next, and then you feed it into your machine or into your automaton, and the automaton just has the state chart or the state machine which we defined. So for Apple, for example, we just follow this state machine, and then each time when we find a word which is allowed, so if we can follow the arrow, the edge, to an allowed position, then we will have a next step. And if we reach this end state, then it's okay, then it's accepted, and if we don't reach it, then it stops. So this automaton, this finite state machine, is the very first essential automaton which you need for regular expressions, and you already know for which languages or for which grammars it is used. Exactly for the checking of single words. So if you want to search something, for example, a single word, you can represent it with this style, and you can search exactly for this word. And therefore, all modern programming languages have these regular expressions, or this implementation of a regular language as part of the language. And therefore, you will find things like that in the programming language, so that you can make combinations of specific characters, for example, with special acronyms, so that you have special shortcuts telling that, for example, this is a word character, meaning an alphanumeric character, followed, for example, by a non-word character, or a white space, or a non-white space, or a digit, or a non-digit, and so on. And then you can define if it is a sequence of the same. So for example, if you make \w and a plus, what is shown here, then it means that this character or this alphanumeric character must be there, but there can be more than this. So we have exactly these rules, replacement several times of non-terminals with terminals and non-terminals. Or if you have an asterisk, then it means it can be there, and if it is there, then there can be also a repeating replacement of the same type. And with a question mark, you can define that it is there or not. So what does it mean? If you remember the intro, I entered a command which follows these rules, and we can have a look at it. So first of all, let's check the rules again so that you see what we need. So we can combine different sets of match points. We can define repeating sequences or existing sequences or alternations or grouping and things like that, so that we can scan files. And I can show you this again with the sample from the intro. So I entered the following command. So, and it exactly follows, so we just focus onto this here. The rest it can be ignored. It's just that we find all log files. Here, this asterisk is also a replacement character like this one, but we focus onto this here. So with grep, you can search all of the errors, or you can search files according to these patterns. And this pattern follows now this definition here. So what must this word have? So what is the allowed word in my definition, in my language? The allowed word which I want to find and which I print then is ERROR, so error. And then we have a \s. What is \s? We have a match with a white space character, and then we have a plus here. So this backslash is a special thing for grep here. \plus means the plus here. So we have \s++, which says we can have several white spaces here, but there must be one white space. And then we have a q, which is q is again a alphabet character. So we have q. So we have error, white space is q, and then we have a word character, alphanumeric word character again. So we have a combination of q and another character, or a q and the number, followed again by white spaces, and there must be white spaces. And then we have a minus, so this represents the character minus. And then we have a 3. So what does it search now, or what are the words which are accepted with this sentence? Are error, white space, q and any character, white space, minus 3 and some numbers. So I search all errors which have a q and a character and all numbers from -300, 3, for example, or whatever. So this is exactly a representation of the regular languages. And if I enter this, then all errors with this pattern are searched. So error QO in this type, -301, for example. So if there would be other errors where the O, for example, is another character, and there is not only -301, or there is -302 or something like that, then also these errors would be searched. So I can also define that at this position we have to define numbers which just have 3 different characters, so that we always search the hundreds positions and things like that. So it's possible with this matching exactly, or having exactly 3 times the same. Okay, so you see, we have with this technique a very, very powerful but not really easy method. but all possibilities which are given by the regular expressions and therefore by the regular languages are part of the programming languages, and they are part of search mechanisms to find file names or to find content in files. And if you're able to understand this, life becomes really easy, because it means that you can easily search for different patterns in files or in file names, and you just have to use one single command. So you can extend this tremendously to whatever you want, and you just need one command. And therefore, checking of formats or checking of files for special patterns, things like that, is very comfortable if you understand this principle. I know that it is not so intuitive because it's really cryptic, but you should understand the general principle, so that you combine characters and you define how often these different characters will appear, and then you get okay or not okay, or you get an output or no output. And therefore the searching mechanisms are part of any computer language or all high-level programming languages. So let's continue with the slides again. Let's have a look not only to words but also to sentences. So therefore, let's do the following thing, that you get another idea of what these different, let's say, combinations of nodes and edges or of states in a state chart mean. In this case, we have here now a sentence or representation of a sentence. So we have a starting point. The starting point, just let's focus on to these gray states here. So we have a starting point. The starting point comes with the. So in this case, I have directly at the beginning here the, so that it comes here to article. The, and then we can have small, barking, big, or fat. So you see we have an or sign here, and this means we can have a small, a barking, a big, or a fat. And then the next thing is that we end up here in adjective. This adjective can then continue with small, barking, big, fat, so that we can make the small, barking, and then let's jump to here, dog or cat. So the small, barking dog hunts the big cat. So if you follow this, you create different sentences which are allowed or not allowed. So if you have not the word on these edges, then the sentence is not accepted by the language. So we have a very simple language here, of course. It just contains of a few different sentences containing barking and fat and big dogs and cats, but it directly shows how this setup can be. So you can also make higher level blocks which represent again something like a state. So for example, let's have a look to here. So if we call this loop here attribute, then we can make a state the article, then small, and then attribute again, dog, and so on. And we can combine these first three states to subject, so that subject, predicate, and then object. So we combine these three parts here to a new state, so that we have a new higher level view onto our graph where we have just three states: subject, predicate, object. And then we jump into, and each step or each state is then again built with other internal small state charts, like here with article, attribute, and substantive. And attribute is then replaced with a repeating adjective sequence. So that a sentence is built by subject, predicate, object. A subject is built by article, attribute, substantive, and so on. So this is again nothing more than a regular language. And if you build all of the sentences like this, you can represent it with regular languages. The problem is that human languages are a little bit more difficult in the case that we will have, let's say, a lot of exceptions. Let's go to the next step, which shows the same graph now as a tree. And therefore, we have the same style here. If you remember, we had the setup that a sentence was built by a graph of 3 elements, subject, predicate, object. And that subject was built by article, attribute, substantive. And then attribute was built by attribute, and so on. So that we now have something what is called a syntax tree. So it's nothing more than the replacement rules. So if you watch, for example, the lower level part here, so if you watch just the first part here, it directly tells you the replacement rule. So its sentence is replaced by subject, predicate, object. And then predicate is replaced by the final terminal word Hans. Okay? So you have exactly the rule, and if you represent it in this way that you always see this as the states, and the states are replaced again by other smaller state charts, as long as you get the final setup here, then you can directly convert the graphs into these formal descriptions and into a way of syntax tree. And syntax trees are really important also to define languages and to check languages. So if we continue, I can also show you some special things about regular languages. If you follow the graph which you saw before, you will see that you will have sentences like the small barking dog hunts the big fat cat. So you have repeating words, and therefore what does it mean? You can create an infinite language, so you can repeat small or other words like this according to the repeating sequence. So if we jump back, that you see this again, so we have this feedback loop at the adjective state. With this we can create several infinite repeating situations, and therefore we can create with a finite set here. So we have just 1, 2, 3, 4, 5, 6, 7 states, so 7 final states. We can create with these 7 states an infinite language. This means finite set of rules can create an infinite set of languages, and this is quite powerful. Also accepted, for example, is the big barking dog hunts the small fat cat. And also accepted is the big fat dog hunts the small fat cat. So you have a lot of possibilities in this case, and it is also accepted that you use the following sentence: the big barking dog hunts the small big cat, or the big fat dog hunts the small barking cat. And here you directly see the difference between syntax and semantics, because syntactically these 2 sentences are completely correct. They fulfill our state chart. So you can follow the state chart and you will see that you will reach the end state without any error situation. But if you read this and if you convert it into your brain, it cannot be that a cat is small and big at the same time. So this is the meaning. So this is the semantics. And it's also that a small cat cannot bark, because barking is something what just a dog can do. So therefore, this is the meaning, the interpretation. We automatically do this in our brain. But again, this is the difference. This is just a representation in our grammar, and this is then the interpretation. This also must be done by a converter which reads your program. So, for example, in a program, if you do definitions or commands, then you will see that, for example, you can create situations which fulfill exactly what you are allowed to do in your programming language. But the commands or the sequence of commands do not make any sense, because they do nonsense. And therefore, there's also a big difference if it makes sense. So, for example, it is allowed, if you have an if condition, for example, it would be allowed from the language syntax that you assign a variable to a constant. But from the sense, from the meaning, from the interpretation, it doesn't make sense that you replace a constant with a variable. So it's just possible to assign a constant to a variable, but not a variable to a constant. And therefore, you have two different steps. First of all, you check if it is syntactically correct, and then you check if it makes sense to do this. So further on, we will see compilers which do these checkings, and then you will see that they have different steps to check the different situations. What is now not possible with these simple languages? So remember, regular expressions are easy and they check sequences of characters. But what is not possible is something which you need for checking, for example, parentheses. Why? If you have mathematical expressions, you have always the same opening parenthesis or brace and closing brace. So you have to count how many you have. So if you want to do this, you would have to do something like what is shown here. So you have a starting point, and then, for example, let's turn like this. So you have a starting point, and then you have open and close. So this is one combination. But if you have another open, you have another close, which you have to find. And if you have another open, you have another close, which you have to find. So in this case, if you have more than these 1, 2, 3, 4 openings, then you have to extend your graph. And each time, if you want a larger number of parentheses, then you have to extend this. And therefore, the language is not enough. So the style of the language, remember, non-terminal replaced by terminal and non-terminal, or by a terminal, is not enough to represent this type of terms or this type of mathematical expressions. And therefore, we cannot do a checking of these expressions with our regular language. So we have to go to the next possibility, and the next possibility is an extension of these simple rules. So if you remember, we had again non-terminal replaced by terminal and non-terminal, or by terminal. What we now do, we replace now a non-terminal by a sequence of terminals and non-terminals. So it's not only just one terminal and one non-terminal or a terminal, it's now a sequence which you can define. So for example, A, B, and terminal, non-terminal, sorry, and things like that. So we extend now this, and what we get now is a context-free language. So the next step from the regular language to a high-level language is the context-free language. And if you think about, you have to count And counting has to do something with, do you remember from the circuits? Of course, with memory. So if we want to count, we had to use flip-flops. And if we use flip-flops, we needed this for a remembering effect that we had in a memory the previous state. So this means we need here not only the state chart and the internal tape, so with an internal input, we also need something what is called a memory. And in this simple case, we can use a memory which is like a paper stack. So, for example, if I take a paper stack, each time if I get a new brace, I put something onto this stack. So, for example, brace open, brace open, brace open, brace open. So I have now a stack. And my end condition of the state chart is now that I have to reach the end terminal position and my stack must be empty. Only if this happens, then the sentence is accepted. Each time I have closing brace, I take something from the stack. So therefore, if a correct mathematical expression is found, I come to this endpoint and I have an empty stack. Okay? It's quite simple. So it's just an extension of the automaton which we have. And the automaton, this extended automaton, is now called the pushdown automaton, because it uses a stack and it pushes always something onto the stack and takes from the stack. The rest is exactly the same. So we have an input tape again. We have this reading head, if we call it like this. So we run with this reading head from left to right. We take always the next character and we check against this graph and we do actions on our stack. So with this, we have now a possibility to represent mathematical expressions. And a very, very, very famous one is the ETF grammar. So the ETF grammar is a simple way to check plus and multiplication terms if they are correct in combination with parentheses. And it looks now like this. And you see here, for example, I marked it again with colors. So you see here again that now the rule is a little bit extended. So this first rule here, E to T, or E is replaced by T, would also fulfill the regular languages. But E replaced by E plus T, so where E is a non-terminal, plus is a terminal, T is a non-terminal, so plus is part of the alphabet, and E and T is again a non-terminal which must be replaced again. So these three, or this combination of three elements here, is not part of the regular languages or the possibilities of regular languages, because now we have a non-terminal, a terminal, and a non-terminal in combination. But it's context free because we always replace it here. So we have no special set, so no special pattern which must exist that we do the replacement. Each time if we find an E, so if for example here there's an E again, then we replace it. So the first replacement rules are E replacing by T or E replaced by E plus T. And then we have T. T is replaced by F or by T times F. So this times sign is, or this asterisk, is again an element of the alphabet. And then we have F is replaced by brace open, E brace close. So these two braces, or these parentheses, are again part of our alphabet, or it is replaced by A, B, C, D, which are then the variables. And what we can get then is a mechanism to check all possibilities of mathematical expressions which have plus and multiplication sign. So here is one sample. For example, we want to create the mathematical expression parenthesis open a plus b parenthesis close times c. And here it's essential that it is not a mathematical interpretation, so we do not take care on the meaning. So in case of a language, the sequence must be exactly this. So it's not c times parenthesis open a plus b parenthesis close is not the same sentence like here, a parenthesis open a plus b parenthesis close times c. So mathematically, and this is now where the human brain directly jumps into the learned scenarios. So mathematically it's exactly the same. You can turn the c in front of the parenthesis term, but in case of the language checks, it's not the same. So you have to exactly find this sentence or this combination, this sequence, and if you find this, then it's accepted. So it's exactly this difference again between the representation or the presentation and the value or the meaning. So if you want now to create this parenthesis open a plus b parenthesis close times c, then we have to follow the following steps. So we start with e. E is the underlined non-terminal, so it's our starting point. So we start with e and go to t. So we replace e by t. T is again a non-terminal, so we can replace it again. T is replaced then by t times f. So this t times f is now required because we need this multiplication sign. And then we can replace t and f again. So t is replaced again by f, and f in this t times f is replaced by c. So if I show it again directly here, so if you just follow always straight line in the columns, then you'll see these replacement rules. So e is replaced by t, t is replaced by t times f, and then you continue with the next non-terminal. F is replaced by c, so f is replaced by one of these variable names, and then we keep the c. So each line is a complete set. You should always have this complete set, so complete valid sequence of terminals and non-terminals. And then you follow again. T is replaced by f, f is replaced by this brace open e brace close, and then we can continue. E can be again replaced, so we have this replacement rule again. E can be replaced again by e plus t, for example, and then we continue. E is replaced by t, t is replaced by f, f is replaced by a, t is replaced by f, f is replaced by b. So we have this sequence brace open a plus b brace close times c. So with this, if we find one way from the starting point to a final completely existing sequence of just terminals, then we have an accepted sentence, and then it's allowed, and then it's part of our language. So what you learn now is we have two different language types. The first one is the regular expression, which just checks single words or small simple sentence combinations. And if you start with counting, so for example, in terms of a computer language, if you have if-else combinations, so you can have a if, and in the if another if, and in the if another if, and in the if another if, so that you will have always and. For each if there must be an end. So each time if you have this counting or this nested combination of parentheses, then you need the next step, the context-free language. So now let's come to the next language. So there are a lot of more, of course, and therefore I just want to focus onto the general part. So there are other specific things in this case, but you should have heard about the state machine which can read other languages, because it's called the Turing machine. And regular expressions or regular languages, context-free languages, are the languages which we generally use in all of the checks for our computer languages. But then you can also find recursively enumerable and context-sensitive languages. So in case of the context-sensitive languages, I can tell you what the difference is between the previous simple language parts and this. If you remember, what did we have? We had a non-terminal which was replaced by a sequence of terminals and non-terminals. So I explained that there is no context around. So each time when we find this terminal, then we can do the replacement. The next step is now we cannot change these things on the right side here. We now have to change things on the left side. And the next step is that we just replace, or that we just apply this rule if we have a special set of terminals and non-terminals. So for example, if we have lowercase a, which is part of the alphabet, uppercase b, which is part of the non-terminals, and lowercase b only if, which is again part of the alphabet. So if we have this sequence of a, something, and b, if we have these only at this situation, we do the replacement. So now we change the left part and we do just replacement if our non-terminal or our variable which we have to replace is in a special context or in a special scenario. And therefore, we have now the context-sensitive languages. And context-sensitive languages directly start with what I said, with a new type of automaton, because do you remember the step from the regular expressions to the next type of context-free languages was the extension of a stack, which is a memory, a simple memory. So you can maybe guess what is the next step. We need a higher level memory. So a memory which is not just a stack, but a memory where we can store anything. And therefore, now it's a complete paradigm change in these things, that we have now also memory which we can completely adapt as we want it. And therefore, we now have the same situation, that we have an input tape, but it's not only an input tape, it's now also an output tape. So we have the situation of an automaton. The automaton is now called Turing machine. And this Turing machine does the following. It starts reading from the tape, it reads something, follows the rule here, so follows the state machine, the edge, possibilities, and also has a definition to write something back. So it does reading, processing, writing back, and going to the left or to the right. Now we have the chance, in the previous state machines or automatons, we just walked from left to right. Here we now have the chance to define where we want to go. We can go right, we can go left, or we can stay neutral. So what we else have to define is that we have an endless tape, because the memory must be endless in our nice virtual world here. And we have symbols which represent not yet set positions in our memory. So we have some special blank symbols or whatever. And then we define an end state and we change this tape, and then we have to reach a special position again here, and we have to reach an end state, and then it is accepted if, for example, we reach a special end state here, end position, if we have a special setup here, and if we reach an end state here. So it's a little bit more complex. But what is this here? This is the memory. So we have now a chance of a simple memory, which is a, let's say, theoretical construction to simulate a memory. And therefore Turing machines are very important to prove or to check algorithms. A formal definition of this Turing machine looks like this then. So we have a tuple of 7 elements where we have, similar to all of the other languages, a finite set of states and a finite set of alphabet. So a finite set of this tape alphabet. And then we have a special finite set of a working alphabet. So we can have more elements which are intermediate states or intermediate alphabetic characters, which are used on the way to the final solution for our Turing machine. And then the transition looks a little bit different. The transition is now not only that we have a state and a non-terminal, a terminal, so a character from the alphabet, which is replaced by a new state. Here we have now a situation that we have a state, something from the alphabet read from the tape, and it is replaced to a new state, a write back information to the alphabet, and a decision to go left, right, or stay at the position on the tape. So the transitions are now a little bit more complex for these Turing machines, and therefore we have more possibilities. And the rest is very similar. So we have a start state and we have a finite set of accepting states or final states. Additionally to all of the other languages, we have all of the other machines, we have one additional symbol, which is maybe called blank symbol, which tells us that a memory element is not yet filled by something from the alphabet. So Turing defined this Turing machine in the year 1936. So let's play a little bit with these rule sets. Let's define a Turing machine, or a simple Turing machine. So the Turing machine has these 7 tuples. We have states, we have a starting state, we have inputs and outputs. So we have intermediate alphabet, things like that. So this is the Turing definition. And we now define this rule set. So the rule set here, so it's here. This rule set is this now. So we have the current position and a character or a sign, which is then replaced or converted in this transition with a next state, the character or sign which we want to write back to our memory or our tape, and the decision to go left, right, or stay neutral. So let's have a look at this. If we are in state 0 is also our start state. So here. So if we are in state 0 and we read a 0, then we do change to the state 0. We write a 0 and we go to the right with our reading head. If we read a 1 in the same state, then we stay at this state. We write a 1 and we go to the right. If we read a blank symbol, so if we reach the end of our input, so that we read a not yet filled memory element, then we write this blank symbol again and go to the left. So this is the first step, but here we change to the next state. So we change to state 1. State 1, the same 0. If we have 0, then we write a 1, go to the left. If we read 1, we write a 0, go to the left, but we keep this state. And in this case, we change to state 2 and so on. So if we have this, we can create our state chart again in a similar way, like what you know from the other things. So if we do this, you will see that it looks like this. So what you have here is exactly this, what you know from the other graphs. You have start state, you have intermediate states, you have edges between these nodes, and you have these definitions. So in this case, you have a start state represented with this arrow, with this incoming arrow to state 0. Then you have these edges here. The only difference now is that each edge has not only the character which is read, it has also characters which are written back to the tape, and you have the decision where to move your read-write head. So in this case, we are in state 0 and we read a 1 from the tape, we write back a 1 and we go to the right. In this case, we read a 0, we write a 0 and go to the right. And in this case, we read a blank, so we reach the end of our input sequence, so of our initial input sequence. We are at the position outside of this, so in a memory which is not yet filled, we write the blank symbol and we go to the left and we reach the state 1. In this state, or in this node, we read a 1, write a 0, go to the left. So we continue until we reach this end state. So in this case, we have the end state here. So it's again nothing more than a state machine where additional things happen. So what we can do now is we can create an initial sequence of characters and can check against this graph if it is accepted or not, or what happens. So let's do this. For example, we start with this sequence 0, 1 and we are in state 0. So we have to the left and to the right as much space as we want, and everything is filled with blank symbols. In my definition, I always start in the most left position, so that we should come back to this position again. And it's not defined for all graphs, so it's up to you how you define this. But in my case, I always start in the most left position. So let's start with this input. We read a 0. We are in state 0. So what do we do? Let's go back. We are in state 0. We read a 0. We write a 0 and go to the right. So what we have now is we have a 0 here again written, and then we go to the right. So the next situation is that we read a 1. We are still in state 0. So what do? We are in state 0. We read a 1. So we write the 1 and we go to the right. So we write the 1 and go to the right. So we have the same input tape like before, but we are now in the position where we reached memory which is not yet filled. So we read a blank symbol and are in state 0. What happens? We are in state 0 and read a blank symbol. So we write a blank symbol and go to the left. Okay? So let's do this. We write a blank symbol and go to the left. Now we are in state 1. So in state 1, we read now a 1. So what should we do? We read a 1. Oh, here we write a 0 and go to the left. So therefore we change this. We write a 0 and go to the left. So we are now in this position and we are still in state 1 and we read a 0. So if we read a 0 here, so we follow this position. So we read a 0. We write a 1, we go to the left and we reach state 2. So if we read a 0, we write a 1, we go to the left and we reach state 2. So now we read a blank. So we are again in the memory which is not yet filled. So we read a blank. If we read a blank here, so let's see what happens. So the blank is here and we will go to the end state. So to the final state here. So we read a blank, we write a blank and go to the right. So we are here at this position in the end state. So we read a blank, we write a blank and go to the right. So now we are at the same position again as in the beginning, but the input tape changed from 0, 1 to 1, 0. So now you can ask, but it's quite nice, but what does it do? So take care, what happens here? So what do you do here? From 0, 1 to 1, 0. What might be the mathematical operation behind? Do you have an idea? You add a 1, a binary 1, do this. So 0, 1 plus 1 is 1, 0. And you can test this with other possibilities. So with other input tapes scenarios. And you will always see that it will add a 1. So it's an adder or incrementer by 1. And if you can do an incrementation and an addition in this case, do you remember? It was essential. Because if you can do this in a logic gate, you can do all of the rest as well. And therefore, it's an adder which describes in principle an addition mechanism. And therefore, if you can do this, you can do all of the rest of the mathematical and also all of the rest of the algorithmic things. So logic comparisons, things like that. So Turing machines are very, very powerful, and they're very, very helpful if you want to check algorithms. So you've seen a lot of different languages now, and you have different types of languages. The simplest one was the language for regular expressions, so these regular languages. And then we created these context-free languages, and we saw that parts of this context-free language, so some of the rules are exactly the same like the regular languages rules. So this means that the complete regular languages, the set of all regular languages, is part of the set of context-free languages. So with a context-free language, you can represent also regular languages or parts from the regular language. And then we came to the context-sensitive language. With context-sensitive language, of course, you can represent all context-free languages, and so on. And therefore, we can create this so-called Chomsky hierarchy. This Chomsky hierarchy is a nested set of language types, starting with type 3, which is the simplest one, the regular language, continued with type 2, the context-free, type 1, the context-sensitive, and type 0, the recursively enumerable languages. So type 3 is with simple state machines, type 2 is with stack machines, type 1 is with memory, and type 0 is also with memory, so that you have these Turing machines. And of course, all languages, also human languages, can represent all other languages, all other formal languages. We focus mainly on type 3 and type 2 languages because these give us the formal background of the formal basis for all of the further working with higher level problem-oriented programs. So therefore, we finished now the first part to explain what is a language, what is required for a problem-oriented language. So we finished this, and now we can come to the elements of a problem-oriented language. You will see that all problem-oriented languages have the same elements. Remember, what is essential for a problem-oriented language? Or what is essential for all higher level languages? You need memory, and therefore you need memory elements. Memory elements like data types or variables with data types and user-defined things like integer, float, boolean, things like that, so that you can define I need 4 bytes, I need 2 bytes, I need 8 bytes, things like that. And then you can have two different versions of memory. You can have a static and you can have a dynamic memory. What is the big difference? The big difference is that in a static memory, it is part of the program. So if you define an array and this array is created as part of the program in the beginning of the program as a variable, then it will be started and you cannot change it anymore. So it will be fixed. You can change the content of this memory, but you cannot change the size of this memory. So it's fixed to the program defined size and it will not be changed anymore. Compared to the dynamic memory, you have something in a so-called heap, which is a memory element which can be reassigned and therefore resized. And the big difference is now that in the static part of the program, you just keep the addresses, and with these addresses you can jump to the position where the real values are located, and then you can read this data from there and you can use it, so you can resize it. In cases of MATLAB, for example, think about everything what you do. You can rearrange memory, you can rearrange matrices, so everything is in the dynamic domain. Well, here we can have a short sample. What is the difference? So if you get an idea of the memory like this, so that you have the memory here. So this is our space in the computer. And then if you start a program, the first program will be stored here. So program 1. The next program will be stored here. So you already know a similar thing which you saw in the previous slides. So this is something like a stack. So therefore this is called the stack memory. If you create now an array, for example, with 5 elements, it is parted exactly at this position in this stack memory. And you cannot rearrange it because here, for example, other program commands exist. And the same here. So if you have different integer values, things like that, they reside at specific positions in the memory. So the difference to the heap memory is now that the rest here can be arranged like you want. So what you do is you create, for example, now 5 elements somewhere here, and you just store the address of this. So the first position here in the memory. So you just need the space which is required for the address, and you can rearrange this. So for example, if you want to have 10 elements, then you create somewhere else 10 elements, you copy everything what you have to the new position, and then you delete the existing one, and you reassign or rearrange the pointer. So it's just a change of the addresses. So therefore these pointer mechanisms are quite, or these address mechanisms are quite important, and therefore you maybe know now why these multiplexers are so interesting, because the multiplexers define addresses in position of memories, or in positions of a space. So what you can now say is it's something like the heap is growing from here, so freely available memory, and the stack is growing from here. What is also a part is that if you always create elements, they will be arranged somewhere in the memory. So you will have a lot of gaps between. And therefore, if you do this quite often, then you will have gaps, and deleting the gaps will increase, so that you have to rearrange these things again. And it's really true that this is a very, very essential mechanism, because with this you have all possibilities. For example, this rearrangement of positions and things like that. And the big difference between computer languages is, for example, that they automatically, implicitly manage the heap, so that you don't have to take care. So for example, Java does this, or that you have to do it manually, so that you have to think about where's the address, so that you do a referencing and dereferencing mechanism between these two things here. This is, for example, done by C and C++. So let's go back to the slides. So the first part, what is essential for high-level programming languages, is that you have memory, and that you have these differences between static and dynamic parts. So static parts as part of the program, dynamic parts which are just addresses somewhere, or space parts in the memory with addresses. What else do you need? Of course, we want to do calculation, we want to do operations. Therefore, we need operators. So basic operators, like plus, minus, assignments, multiplication, all of these things. And additional operators like referencing, dereferencing, indexing, things like that. And of course, we need something which gives us a possibility to make decisions. So for example, if something happens, then do something else. If something does not happen, do a different way of the program. And we want to repeat things. So we need a control about the application workflow. So we have to decide, if something is true, then do this, or while something is true, repeat things several times, or count as many iterations and then stop. So all of these things is also part. So all of the programming languages must have memory, operators, and application workflow control. And of course, they must have possibilities to do an input and an output, so that you can get in contact with the external world, so that your user or your customer can enter some things or can give you a file with data so that it can do processing. So input-output control is also very essential. And there we are directly again in the operating system style, because the operating system hides all of these things so that we can get to the hardware and that we can get to interaction mechanisms without any knowledge about the internal hardware specific patterns. So therefore, for higher level languages, we need these operating system mechanisms and also these system calls. And then all of the higher level programming languages offer a special mechanism to structure your code. So this is also part of the definition in a formal language, so it must have a special structure. For example, you have begin and end signs. In MATLAB you have if and you have a corresponding end, or in C and C++ you have this curly brace open and curly brace close, things like that you have blocks of logical combinations. And you can have the structure that you can split the code into pieces. So if you think in MATLAB, you have scripts and you have functions. So scripts and functions are the essential part to bring your code to a smallest piece, which is then operated, so that you structure your code in testable functionalities. And therefore you have functions like usual mathematical functions, or you have just small procedures which are in principle nothing more than script pieces, so sequences of commands which you can run. And then of course you can split your code into different files so that you have a structure of different files. So a large program with millions of lines of code follows this stuff. And then the rest, so if we go back, for example, all programming languages have this memory operators, application workflow, input output, and basic source structuring, and the rest is then just based on specific, let's say, structuring mechanisms, which are then extended to have a different scoping or a different view onto special pieces of the code. And this is then where you jump into the object-oriented style, where you have, for example, higher types, so that you can define your own types, so that you don't have just your basic elementary types. You can define your own types based on classes. And then you can also inherit specific parts of this class, so that one type inherits information or structure from another type, so that you have no redefinitions of things. You can also define your own operators, so that plus can be overloaded with new functionality. For example, if you define a type vector, the vector contains a sequence of elements, and this sequence of elements should be added. They can define now an operator which automatically adds the complete vector, and not so that you don't have to write your own for loop each time if you want to add, for example, vectors. You can just use a plus and vector plus vector, and implicitly the for loop is internally operated, and you get the result. And then you have things like higher namespaces or other concepts like templates, so that you can have a type independent mechanism of classes. So for example, if you have a mechanism of container where you can store information that is unspecific for a special type, you can store their text or integers or whatever, so that all of the operations really run on this. And it also extends error handling, so that if there is a memory error, for example, that you get an exception or things like that. So you saw that all programming languages have the same structure, the same elements. So therefore, what is the big difference between the languages? And therefore we have to think about where or how can we classify special types of languages? And therefore we will focus now on the classification of languages. And there are several of classifications, but the main parts can be seen like this. First of all, we started with something like assembly. So what is it? It is just a sequence of commands. And therefore, it's a sequential unstructured programming. Unstructured because you have loops which are defined by jumps to other positions in the line counter for the program. So it's not so nice separated if you compare to what we discussed before, that we separated into small functions and things like that. So higher level assembly, of course, has these things, but the basic thing is unstructured. So we have a sequence of instructions with jumps to dedicated code positions. So the next step is procedural programming or structured programming. Procedural programming means you split now these unstructured things into small pieces like scripts, and you run the script. Each time you want to do the same, you just call the script. So this piece of code. So you split it into these procedures, and in a special, very special focus, you use functions. So like mathematical functions, you have a function name, you have return values, and you have input arguments. And you do something with the input arguments and give back the return. So this is the structured programming, which is a subset of this procedural programming. So these are two essential things. If you have more or less assembly thing, or let's say structured way like C or whatever, then you know, okay, this is this class. If you have more structure or more additional concepts like templates, classes, own types, own operators, things like that, then it jumps from here to here. So with object-oriented style, you can do the structured programming, and with structured, you can do also unstructured programming. Okay, so it's always a subset. So in this case, object-oriented programming extends these mechanisms to a more, let's say, essential structure which you have to fulfill to really write object-oriented code. And therefore, you have additional mechanisms to check. So for example, if a memory element, a variable, is part of a special class, a special type, then you just can do the operations which you're allowed to do, because it's defined here in the scope of this class. And therefore, you have a better structure, because others or other external code parts cannot just call what they want to call. They just can follow the things which you define that they should do. So they have to use a special interface. So this interface definition here is a very, very essential part. Here it's more a loose or weaker scenario. So you have modules, for example, you define files which contain file access. So code files which have the file access functions, but you can call all of them. In this case, it's really fixed on the object, and each object or each class, each type, each new type has everything what it needs inside, and it is checked if you do not access things which you're not allowed to do. So with this additional structure, you have more availability in the compiler to do higher level code checks. And then I have two more which are not so relevant, but which are interesting in the case that they extend these mechanisms. One is the aspect oriented programming. It's not so relevant anymore. In this case, you have special patterns which you use to extend your code automatically. So in this case, you have a object-oriented program, and then you can find special patterns to extend code with things which are not directly part of the usual code. So for example, if you want to do debugging, so debugging is just an addition to what you really need, and what you really need is here. So, and you want to give the customer only things which he really needs, but not things which you needed to debug the things. So therefore you can define aspect-oriented cross-cutting concerns, so that you define patterns, and then each pattern, for example, at each jump point where you go into a function, you can add additional checks or outputs or whatever, so that you see the flow through your code, things like that. And another thing is a more data-driven or data flow-driven view, or graphical programming style, so that you have another layer on top of your programming where you can do the design, and then you can directly check your design and can do the programming. It's a little bit a different aspect, or is a different paradigm, because here you're focused on data. It's like a circuit-based version of programming. So if there is the data arriving, so the data flow gives you the next step, then all of the different program parts will react on the data. So like with the electronic circuit. So there are different styles. You will find a lot of these classifications and paradigms in the internet, but I would say these are the most essential one, where the first three are the really essential one, which you find in any appearance in different languages. So with this, we have now a possibility to identify things which belong to a language. We can classify a little bit the languages. We know what is behind the language, and therefore if we combine all of this, we can now do a creation of a program which understands the language and checks the language and creates then the assembly, because on the back side of all of these programs is we need machine code, and this machine code must run on a specific hardware. So it's not gone away just jumping onto higher level language. The lower level things which we learned are still inside of these discussions. So therefore, let's have a look what we need. Do you remember that as we started with assembly, that we needed a program or a software part which converted the assembly into real machine code or into a usable machine version? It was called assembler. So we needed an additional package which was started and fed with the commands, and which brought it into a usable way, so into a target code. The same is now here. So what you have here is now the flow through a so-called compiler. So we have our source code. So each compiler must fulfill the things which are required by the individual language. So it must check the required words, it must check the required structure, it must check if it is semantically correct, and it must then do the conversion to the target code. So therefore we have a compiler always for the specific language. And in this case, we do the steps which we already know from the grammars. So here, a first thing is we do a scanning. Scanning means we check the individual parts. So we identify individual words which might belong to our language, and then we can use these words in a combination of syntax. So finding words, regular expressions. So here we have a lexical analysis, we have the regular languages part here. Then we identify the word, so we create a so-called symbol table. The symbol table is in principle something like this the syntax tree. So we have a table with all of the symbols and the structures to each other. And then we check the grammar, so the structure. Do you remember we have if-and combination, we have nested if-and combination. So what do we need? Of course, we need context-free languages. So at this part here, we do a syntax check, a syntax analysis. And this is called parsers. So a scanner detects the words, or the tokens in this case, a single identified word which follows a special syntax, or which is used for the syntax, is called token here. So the token goes to the next step, which is the syntax analysis. So this is regular and this is context free. And then we do a semantic analysis. The semantic analysis needs a little bit more. So here's a little bit of, let's say, Turing machine is not completely correct, but you can think about, so we have to interpret, is it logically allowed, or is it from the interpretation allowed, for example, to do this operation? For example, is it allowed to assign a variable to a constant, or is it not allowed? So it's not allowed, of course, but syntactically it's correct. So we do a semantic check. So we have semantic procedures which check if it is allowed, and then we create an intermediate code. This is used that we don't have to write a complete compiler or complete thing for all of the different hardware sets. So different hardwares offer different possibilities, and therefore with this step we have an intermediate language which can be easily converted to the different hardwares. And then we do a code optimization. So for example, if you think about this pipelining, so if you can directly identify to not to interrupt this pipeline, so that you can optimize for loops, or that you can skip for loops, or things like that, which you automatically understand in case of an analysis, of a very specific analysis, you can automatically optimize things. For example, C compilers have different optimization levels which you can activate. And then you do the real code generation, where at the end the target code, which means the machine code, is the result. And if one of these steps fails, then you have the error processing. How can you create these things that it, or how can you check if it fails? Of course, there are state machines. State machines have always clearly defined situations. So if a special accepted state is reached, perfect, you go through it. If a state is reached which is not accepted, you go into this situation of an error processing. So you have state machines in this compiling step, and this is everything what you need. So you have all of the computer languages stuff here, and for example, if you do file programming and if you have own formats, in principle the format definition just follows a formal language. So if you know these things about a formal language, file reading or special format reading like XML or whatever is quite easy, because you just follow the formal language and you can directly check if it is correct, and you can directly identify single elements. So now what is still missing? Still missing is the following: a linking process. So we created now different files as a version of target code. So we have different target codes, we have different modules, and now we want to combine it to one executable. So we want to combine it to one running program. This method helps us that we can use external code. So that, for example, if your colleague wrote code, which you can also use, that you just compile it and then you combine it to one executable. So you can use libraries. And therefore, you have always two steps: the compilation, which creates the machine target code, and the combination, so that you create one executable out of different sources. And therefore, you have always this compilation and linking. And there's now a small difference. Nowadays, it's not so relevant anymore, between compilers and so-called interpreters. So all of them, both of them, do exactly the same. They take commands from the source and they convert it to machine code, but they do it at different times. So let's check compiler. A compiler reads the source code, compiles and links and creates an executable. So all of the programs, all of the Office programs, all of the things you use here on your computer, or all of the apps, are in principle executables. So they are small pieces of already compiled programs, and then you start it. So it's really essential also for licensing, because you don't see the knowledge or the technical realization, so you cannot easily copy this. So therefore it's really essential for also for licensing. So, and then you start the executable, so the program starts and it loads the also converted or the predefined libraries, which are also already in machine code, and then processing is done. So this costs time, and then the startup is quite fast. On the other hand, in an interpreter, you write the code, and then the code is interpreted at that time when you start it. So you start the program, you do the compilation and linking, so the things which you have done here. The same things, it's not necessary anymore to have it command by command. It's also, you can do it for the whole program, and then you do the loading of the libraries and the processing. So for the startup, you need more time here, and therefore it's also essential if you, for example, compare different types of programming. The program itself is quite fast, so you can program with different versions of programming language in the same optimal or optimized way. But the startup can be different. So startup of interpreter programs can be slower than others. So for example, a version of the compiler would be C, C++. A version of the interpreter would be, for example, MATLAB. Okay. With this, we come to the final thing here, which is comparing software languages, so that you get an idea of what are really the differences of languages, so that you see a little bit the differences of languages. And what you should learn here is that if you have the knowledge about programming in one language, that it will be also quite easy to write other programs or to understand other programs, to get the complete skills of a programmer in this new programming language. So with this all small specific speeding up things and things like that, it's a little bit a different story, but it's quite interesting that it's easy to understand and interpret or read other programs in other languages. So we want to compare the languages C, C++, and Python. So if we take care in the compilation or translation between the language and the assembly code, we have two compilers. So C and C++ is a classic compiler, so that you get an executable at the end. Python can also be used as an interpreter, so that you can enter commands directly, and each command is operated or run when you enter it. So that you have these different styles, and also in the programming paradigm you have differences. The programming paradigm is the classification. So C is a classical structured programming language. C++ is an object-oriented programming language, the same like Python. But in C++, you have a very specific thing, because C++ is an add-on to C, so that you have a whole C also in C++. So you will see a lot of C++ programs which are in principle structured programs. In the history, you can find a long history of all programming languages. I won't go into detail to this. C comes from B, so therefore the letter C. C++ is a combination of C, Simula, and other things, and Python comes from other programming languages. So the history of C is the longest, is in the 70s so 1970 around. C++ is about 1980, and Python is the youngest in this compilation, where you have 1990. So, but there's a long history already now, where you also see the trends of the different paradigms. So all programming languages started with this unstructured, and it came to the structured programming, then to the object-oriented programming, and therefore you see this history also in the languages. According to the basic structures or the organization of your code, you have in C different files with functions, and functions contain blocks, and you have these blocks also for if-else constructions, while loops, and things like that. The blocks are characterized with the curly braces. Similar to that is C++, but it extends this structure with the object-oriented parts, so with namespaces, with classes. And functions are called here methods, because methods are interface setups for the classes, so that you have interface access points, and therefore it's called methods. Also, the blocks are identified with curly braces. And for Python, it's very similar to C++, so that you have this object-oriented style. If you continue, and if you take care on the different things which are part of a programming language, then we can start with the memory elements. So in memory elements, you have different types. C and C++ is very similar. You have short, int, long, float, double, all of these standard types. And in C++, you can extend these types so that you have already a standard library, a standard template library, which extends these different classes or by different classes, so that you have, for example, strings, lists, vectors, things like that. Python has a dynamic typing, so it automatically makes things right here. So it's a little bit the difference to the rest. A little bit similar to MATLAB. All of the values have to be stored in variables. The variables are of a specific type. In the object-oriented style, the variables are called objects if they are from additional classes. So if a class defines the structure of the variable, then the variable is called object. So therefore, this object-oriented style. So it's an instance of a class. A sample here is if you have arrays, then you define, for example, int array with 5 elements. This is exactly the style for the stack memory. So if you have it available in this style, it is created during the start time of the program. The same is for C++, and very similar is for Python. The only thing is that you create a variable with these zeros, similar to what you know maybe from the MATLAB. The big difference between Python and C and C++ is that you have, or that there's a big focus on pointers in C and C++. Pointers are nothing more than the addresses, so the access to the heap memory. This is done automatically in Python, so you have these high-level data types, and you don't have to take care of this. In C and C++, you're more oriented onto this address and memory management things, and therefore you have this structure of types. So therefore, I want to explain again what is this specific thing. So do you remember I painted this heap and the stack memory on our external camera? So you have an address in the stack which points to the heap. So this should be shown here again, where you have this situation. So you have somewhere an address and you point to another memory, or vice versa. It depends on. So what does it mean? You have somewhere the address. The address is referenced or is named like this. You have this asterisk, int asterisk b, for example, means it's an it's an address of the position b. And then if you want to go to this, then you have to do referencing or dereferencing. So you have to follow this address, and then you will come to this memory element where really the data are stored. So for example, you can create a stack element, in this case int a equal 5. So this means you have a stack element named a, and this stack element named a contains the value 5. And then you make an address which points to this. So you take the address which is classified with this AND symbol. So you take the address of a and assign it to the address or to the pointer value to this address. So therefore, this is the big difference. Here you just have the pointer of A, and if you do a dereferencing, then you can go to this value. So if you make asterisk B, then you will get the value. If you make B, then you get the address of this value. And it doesn't matter if the value is in the stack or in the heap. Usually you have it in the heap, because then you can do a rearrangement. So you have the real value, and you have the address where the value is located. And this is very essential for C and C++, because this memory allocation, memory management is very essential for these languages. The rest is, again, very similar. So remember, we had as another thing that we want to do operations. So we need operators, assignment, plus, minus, multiplication, and so on, or logical operators. So there are small differences in the naming. So for example, in Python you have an AND, and in C you have a double AND symbol to have the logic AND, things like that, but the rest is very similar. And then you can have additional operators. For example, in C you have a plus plus, which is an iteration by one, and things like that. So that you have small differences, but a lot of similarities. Interesting is that a big difference between C, C++, and Python is the structuring. So you have, of course, the blocks, but the blocks are identified with curly braces in C and C++, but in Python you have the identification with an indent. So to show this here in the sample, for example, the if part, this block is done if this if statement is true. So it's the same if condition, and then this is true, then do this, else do this. So if you remember in MATLAB, it's very similar. You only have no curly braces. You have if and then an and, so that you know, okay, this is the block which belongs to each other. This is the same in C++, but in Python, the identification, what belongs to the block, is done with this indenting. So you have the number of white spaces in front, which tells Python that it is now part of this block, or that the new block starts. So if you have here another indent, then you know, okay, it's a new logical combination of commands. The rest look quite similar. So if-else constructions are quite similar. You have this if-else possibilities, things like that. Also for loops, you know maybe that there are different loops. You have a while and a for loop. A while loop is a conditional loop where you have a special condition, and as long as this condition is true, the loop will be operated. In a for loop, you have more or less a counting loop. So exactly number of times you repeat the different sequences in the block, and therefore you have different loops. C and C++ also offers you a do-while loop, so that the check of the condition is at the end, compared to the normal while loop where the checking is done in the beginning. This is not available in Python, but the rest is very similar. The only naming or the specific thing is the syntax, so that you directly see what it is, but the syntax is slightly different. For example, in C you have for brace open I equal 1, as long as I is smaller than 10, do I++, so always iterate. And in Python you say for I in range from 1 to 10, do this repeating. But you see, there are a lot of similarities, and there are also differences. And as there are always some similarities, you can design things automatically if you know, or if you do block diagrams. Do you remember the tutorial? If you remember the tutorial, we created a block diagram like this. So I put it to the external camera so that you see it. And in this external camera, you see this block diagram, which we used for the definition of our steps according to an operating system scheduler. So we did different blocks, single operations or combinations, and then we made a decision, so if it is the idle process or not. So you can see this in the tutorial, and this is exactly what you can do, because you always have if conditions, you always have loops like here, so therefore you can define standardized methods to represent these things. And this is what I want to show you, because you will come to these setups in several programming developments. So what you usually have is a standard process block, which is an action. Action means a single command, or maybe also a combination of commands if you have combination blocks. So an example is, for example, turn on computer, things like that. You have two very famous representations of that. You have this Nassi-Schneiderman diagram, and you have the UML Activity Diagram. So there are two different styles, but they always show the same. So it's up to you what you like more, but also you have this for documentation availability, so that you can do your documentation of your code. As I said, the standard block is like this. You have a rectangular block, and this defines the action, and you write into this block, you write what should be done. So the next one was a condition, so if-else condition. So in this case, a condition looks like this. You have a specific question. So the question is here, for example, Wikipedia loaded, and if it is true, do this, and if it is false, do this. So this is a very famous representation of if-else conditions and of code. On the other hand, UML activity diagrams have this also here. So the condition is now in this different style, and you have again two possibilities, true and false. What else do we have? Of course, loops. So we have different loops. We have a loop where the question is a while loop, for example, where the question is at the beginning, and a while loop where the question is at the end. So let's have a look at the differences. In the Nassi-Schneiderman diagram, you have again such block diagram, so that you have the condition in the upper part, and then you have a combination of the different commands which should be operated during this loop. So you see these two sequence elements, search for articles and read article. These two things are part of this loop, so that as long as the diagram understood, you do this. Or on the lower part, open newspaper, read article, and then article understood is again, these two commands are operated as long as this question is true. On the other hand, the UML activity diagram just follows the same. So in principle, a loop is nothing more than a if condition, and then an operation sequence, and then a jump back to this if condition. And as long as this if condition is true, we do this. And therefore, you can also convert for to while loops and while to for loops. So it would be enough to have one of this type here available. So it was just a short explanation of representation possibilities. Let's finalize our comparison of software languages. So you can also have a look into flexibility of the different programming languages, because you cannot say I just want to learn C or I just want to learn Python. All languages have advantages and disadvantages for specific things. So in this case, C is very flexible, is a low-level programming language. You can do the hardware programming up to almost graphical user interfaces. it's easy to learn. You can have far success or success. So it's a very portable and compiler-based thing, but you have differences between different operating systems, of course, like that. C++ is very similar to C, but it extends these object-oriented styles. It's in some cases a little bit slower than C, but it's easier to maintain by teams of with a lot of people. You have an easy project management, therefore, because you can directly identify the interfaces, and then you can directly separate tasks so that different developers do different tasks. And Python is also very flexible. The easy or nice thing is that you directly can enter commands so that you have this interpreter style. So it's a very portable code. You don't have to think about data types, things like that. So it's very open, and therefore the community in the science world is very, very big. If you watch into these possibilities, then you directly find things which tells you for which special cases you can use this language. So for example, C is very often used for operating system, for low-level hardware-based things, for all types of applications, where C++ is more used for higher-level things like games or user interfaces, graphical user interfaces. Though all of these higher-level user interfaces with graphic output is usually done in C++. Python is very, very comfortable for university tasks due to the plotting. It's similar to MATLAB, a few commands, and you directly can plot things. It's a script programming language, so everything what should be done regularly and should be controlled by a special program can be done with scripts. It's nice for prototyping and for web applications. Finally, if we do these programming things, I want to just show you a little bit the differences again between structured programming and object-oriented programming. It's just an extension which should give you a little bit of feeling of what is the difference. It's not that I want to show you everything here, so that it's not a complete overview what is really the big advantage of object-oriented programming, because it's really a paradigm change, and therefore it's in most cases really difficult to learn. It's easy to learn this structured programming. In some cases it's really difficult to learn the object-oriented style. So let's have a look onto how we structure our code. So we have modules. Modules are in principle files which contain always the same type of functions. For example, we can have a module which does all of the file operations. So all of the low-level file operations like open file, close file, read text, write text, things like that, read binary and so on, is the end of file reached. All of these low-level things are reached here, or are contained here. In C, for example, you always have a separation between a definition and a declaration. So the declaration just contains the interface, which is the head of the function. So it defines the return value, the name, and the handover arguments. And then you have the definition, and this definition assigns a block or the commands which should be operated if you call this function. So you have always two files, a header and the body. So h file, so with the extension h, for example, in C, and with the extension c in C. And then if you have higher level interfaces or higher level services, then you create a new module, and this new module again contains or consists of two parts, the definition and the declaration, and it uses the lower level things. So there is no restriction, anybody can do anything. And if you now want to open a file, for example in a main program, you have to create a pointer which points to the file. So here you have this structure of the pointers again, and then you call eRead text file which calls something from here and goes then to there. So let's have a look into this. So it calls this, runs this body, and in this body the lower level functions are triggered and then they run this body. So it's a really easy separation, but there are no restrictions. You have the setup of lower level interfaces or services to higher level services, which are combined then in the main program. Internally necessary variables are usually seen also externally. So this means that if you have a file pointer which represents the access to a file which is required here, you will always have to keep it in something like a global memory. And this is the difference to the object-oriented programming. In the object-oriented programming, so it looks in the first view very similar. So you have again the declaration and the definition, so an HPP and an CPP file, for example. But you have now a new structure which is called class. And everything what is inside of this special namespace, inside of this special block, just belongs to this special class. And the class is directly a type for an object, so for an instance or a variable of this class. And then you have everything what is required by the class. So all variables which are required by this class are part of this class. So now the file pointer is part of here. So the main program does not need any knowledge about where the current position in the file is. So everything is stored here. And you can define if something is private, protected, or public. So if it is only allowed to access it internally, or if others which are related to me can call it, or if everybody outside can call this function. So this is in principle now a real interface for everything what this module can do. And then you have this lower level setup, and this lower level setup is then inherited to a higher level service. So all of the functions here are also then part of this new class. So you can directly call, if you create an instance, so an object of this class, you can directly call also functions from here. It depends on if you made it public, protected, or private, of course, because only public things can be called directly outside. Protected things can be called by an inherited situation, and private things can only be called by the same class. And then if you want to do this file reading, then you do not do it like here, that you have this file pointer externally available. So if you manipulate this, all of the rest will be interrupted or will be in a crashing situation. Here you just create an instance of this new type. And then you can call with this instance name or with this variable name. So you have a new type in principle. And you can directly call with this dot, like in a structure. You can directly call a function from here, which calls then the function from here. So it's very similar again. The only thing is that you cannot manipulate, for example, the file pointer from external here. So you don't have a direct access to this information. Here you directly have access because it's really the address. Remember what we said about the address? The address points directly to this value. So in this case, you can manipulate it. So if something fails outside, also the functions here will fail. In this case, everything is inside. So you cannot manipulate it from outside, or you just can manipulate it if you use these functions, or in object-oriented style, these methods here. Okay? And this is a big difference, because then you have really something which gives you protection, and therefore you can share, you can take this and give it to one developer, and he can or she can develop this, and then you get it back, and everything what you define in this interface is allowed, and the rest is protected. So you have the possibility here to internally protect variables, methods, and things like that. And you have a possibility to directly have a way to represent this lower level, higher level services, because you can, in this case, you just do it by the definition of the files. In this case, you directly do it with this inheritance. So you directly inherit lower level functions, so that you have it available here also in this higher level programs. And this is a very, very useful thing. So let's have a look into this thing directly as a combination, so that I'm not in front of the image. So you directly see now these differences. So it's very similar, but with the structure, with this additional structure of the code, you get an additional possibility that compilers or other checking mechanisms in your compiling workflow can prove, for example, protections of variables and methods. Okay, so that's all what I wanted to tell you about programming language today. If you search the internet, there are several other informations. For example, the history of languages, like here starting with Fortran, and all other languages are in some case related to these things. So you have a lot of relatives in this case to the modern languages. Okay, you will find these things in the internet also with a lot of more information about languages. We can also search for the Hello World program, which is then represented in different programming languages, and you will be surprised their languages, or their names of languages, which you should never use in an application for a job. Okay, search for it, you will be surprised. The easiest one in this case is maybe white spaces. So you program with the different types of white spaces so that you see nothing on a screen, but it will do, for example, a plotting of Hello World. So it's strange. I want to say you stay safe. I know that things are difficult in this theory of programming languages, but nevertheless, it helps if you want to check formats of files, or if you want to search in files. So again, stay safe and don't lose your head.